I'm Russ Altman, and today Professor Eric Dunham describes how he simulates earthquakes, volcanoes, and tsunamis in order to understand the basic physics of how they start and how they propagate. He will tell us that we can expect advances in understanding where the most dangerous earthquakes may occur and how they will impact humans, but he's not, because of so many random factors, he's not so confident that we'll be able to predict precisely when the earthquakes will come. It's the future of earthquakes. Eric will tell us that there have been big changes in earthquake science, and it really relates to the placement of sensors at the bottom of the ocean. Some of these are passive and they just collect data, and they're picked up. You open up the data and you do an analysis of what's been happening over time. Others are linked by fiber optics and are giving real-time data about shaking of the earth. Computational modeling allows Eric and his colleagues to do what-if studies to say where are the earthquakes likely to happen, and what kind of earthquakes? Will they be multiple small ones or a single big one? Earthquakes may or may not be on your mind. If you live in California or Japan, you literally organize your home with the possibility of an earthquake in mind. No big bookcases near the bed, no glass frames near your head. Folks in other areas may not worry about earthquakes. They're more concerned with hurricanes or tornadoes or whatever. There are regions of the world that have a history of earthquakes, and these are often adjacent to active volcanic areas. Both volcanoes and earthquakes can cause enough movement to shake and cause tsunamis. And in the last 20 years, we've seen the terrible consequences of all three of these around the world. Professor Eric Dunham is a professor of geophysics at Stanford University. He studies the physics behind these major geological events, and he simulates them in computers. He can help policymakers understand what kind of earthquakes they may have in their area and what kind of building codes they might want to create in order to protect people from those earthquakes, and as well as volcanic and tsunami events.
So my background is in physics, especially theoretical physics, but I just found myself increasingly drawn to real-world problems, large-scale things that really matter to society. And so the field of natural hazard modeling and natural hazard science in general just really attracted me to it. It's a place where we can take scientific computing, large-scale simulations, connect them with data, and really try to understand how the world is working.
Yeah, and that's an important point that I wanted to get to pretty early, which is what has changed in the last, say, 5 or 10 years that makes us, I believe, we're optimistic that we're going to make a lot of progress in understanding these things that have been with us for 100 years, and I think many of us still consider that these are kind of random events with almost no warning. Are things changing?
Yeah, there's really two things that make me just extremely optimistic about this next decade. The first is the growing power of computers. I've seen the field transition from two-dimensional modeling when I started in graduate school some 20 years ago, now to really high-resolution three-dimensional modeling of real earthquakes. So that's the first thing.
Let me just interrupt you there. What would two-dimensional mean versus three-dimensional? If you could just give me a little bit more on that.
Sure. Two-dimensional modeling would be, let's say you have a subduction zone, a place where one tectonic plate is diving down beneath another, right? And it's going to create the world's largest earthquakes, tsunamis. A two-dimensional model would take that and just make one vertical slice through it. And it would assume that the same thing's happening indefinitely in that other direction.
So you kind of pick the key region, make a cut in it, and then look at the physics of what's going on in that region. That would be a 2D model.
That would be a two-dimensional model.
And then in 3D, I guess now you're looking at the whole three-dimensional structure of the two plates and how they're rubbing against each other, et cetera.
Exactly, yeah. And the real world is 3 dimensions, and that's what it takes to make sense and to connect with data.
Okay, so now we got the 2D, 3D thing. Please continue. What are the opportunities and right now?
Well, the second big advance has been observations, data, sensors. And in the case of a subduction zone where these giant earthquakes and tsunamis are happening 100, 200 miles offshore, now we have the ability to put instruments on the seafloor. And in some cases, even stream that data through fiber optic cables back to land. So we have this really unprecedented view of what's happening.
Yeah, I wanted to ask you about the sensors because it sounds fantastic. And what I can't tell though is should we be excited about those sensors because they're going to be part of an early warning system, or are we excited about them because they're giving us baseline data about how the physics works all the time, not so much worrying about when the big earthquake's going to come, but just seeing the normal physics of the Earth?
Well, it's both. So it's obvious it's cheaper to install sensors that are not direct cabled back to land. And so those types of sensors, they would be deployed, left there for many years. We'd gather data, hopefully catch earthquakes, at least smaller ones, maybe even larger ones, tsunamis. And we'd use that to figure out what happened. How did those earthquakes move the seafloor? But in some cases, offshore Japan in particular, the country has invested in these fiber optic cabled networks, and they're using that data, or will be using that data, for actual tsunami warning purposes.
Okay. All right. Great. Okay. So that paints a really good picture, which is that we're excited because we're getting more data, both passive, what I might call passive, where you collect it later on and reconstruct history, and then the active one that's giving you real-time data like in Japan. So now let's go back and let's just define some basic terms. Tell me about how should I think of an earthquake? You were talking about subduction zones and things moving. For people who haven't thought about the actual physics of a earthquake, tell me, when you look at these things, what do you see as a physicist?
Sure. So you can think about the outer part of Earth as really hard rocks. They're solid, they're brittle, and they fracture. And so there are certain places where these rocks are heavily broken up, they're weak. And so as the Earth's interior is moving and pulling on the surface, there's sliding that takes place across these surfaces of weakness. And so those are earthquake faults. And what we've discovered is that these faults, most of the time, they're remaining locked. The two sides of the fault are coupled together. As the tectonic plates move, the rocks are surrounding them are being bent to form stretch, right? Energy is being stored in those rocks, just like stretching a spring. And then suddenly, pow, the fault slips. All of that energy, or much of that energy, is radiated out as seismic waves, turned into heat. And so those waves, as they propagate out, that's the damaging shaking.
Okay. Great. And if I understand, most of your work focuses on the Pacific Rim. Is that true? Kind of North America on the West Coast, and then Japan. And what is special about that part of the globe? Is it just that the Pacific Ocean is the biggest ocean, or what? Why is it that we have so much activity in that little ring?
Right,
Big
so there's
ring.
faults that occur onshore, like the San Andreas Fault. And I've been interested in those for a long time. But most recently, my work has shifted offshore to subduction zones. So this is where one plate dives down beneath another. And that's where you get the magnitude 9 earthquakes. That's where you get the giant tsunamis like we saw in the 2011 Tohoku-oki event in Japan. So these types of earthquakes tend to occur around the edge of an ocean, where an oceanic plate is diving down beneath a continent.
So what, and I was thinking, I obviously I knew we were going to be talking, and I was thinking, what are the key forces that you have to think about? And I am so clueless about this. I was wondering, like, does the weight of the water in the ocean matter? Does the moon matter? I know that there's internal dynamics of the magma in the center. What are the key physical forces that you have to worry about to get kind of accurate simulations?
Well, what we've recognized over the past, it's probably been 20 years, where we've had the growing resolution of what's happening on a fault. And so the previous thinking that was developed over 100 years ago was that these faults would remain stuck, locked, coupled, 200, 300 years, and then they'd slip in an earthquake.
Okay.
And it actually turns out it's much more subtle than that. So there are some parts of the fault where that is true. They're 100% coupled in between earthquakes, but there's lots of other parts of the fault that are slowly creeping, so slowly that it takes extremely sensitive sensors to pick that up. And so what's emerged is this very heterogeneous, this patchwork nature of the coupling on a fault. So some parts are locked and coupled, building up energy to release an earthquake. Other parts are slipping. And we really don't know what controls that variability. And we don't know if the parts that are locked right now and that have had earthquakes in the past, are these going to be the sites where we have future earthquakes?
So great. So it is. the models are rapidly changing, and now I can see why all of that sensor data would be so useful, because it kind of allows you to confirm or refute different theories. How are we? I mean, it's taken us 9 minutes to get to this question. How are we at predicting earthquakes? And is there some magic bullet? Is there some piece of knowledge that you would love to have that would be a breakthrough in prediction? Or is it really a much longer slog, and we're not very close to prediction?
So I think what our computer simulations have shown is that an earthquake once started, and these earthquakes are happening all the time. Small earthquakes pop off, a small earthquake will pop off once every hour here in California, but most of those don't grow to become big earthquakes. So it's really more of a question of what keeps an earthquake small and what allows, every once in a while a big one to get really big.
Yes.
And our simulations show that these earthquakes are just extremely sensitive to small-scale details. And I'm not optimistic about ever knowing what's happening 10 miles underground to be able to say an earthquake's going to stop here or grow a little bit larger. What I am excited about is so that would be prediction, knowing the exact timing of an earthquake. I am excited about predictability, right? Putting instruments on the seafloor, mapping out these regions where the fault is coupled, where it's not. And then it's really an open question, a hypothesis now that those regions that are currently coupled are going to be the sites of large earthquakes. And you map out which regions are coupled, and you know how large that earthquake will be.
Right. And you can see that even if you can't say it's going to happen next Tuesday or 5 years from now, even knowing where the danger zones are, the areas where you're expecting, it would be, I would guess, super useful to be able to say, I'm expecting a bunch of these small adjustment type earthquakes versus I'm expecting a big motion at once, because that would allow policymakers to think about how do we build infrastructure and where do we place people. That actually led me to one of the questions, again, out of my cluelessness. Does climate change or global warming, does that have any impact in current models of earthquake either starting or propagating?
So most of what's loading these faults and causing Earth's plates to deform and bend and build up stress, release it in earthquakes, are large-scale processes happening throughout Earth's interior. Climate change changes in seasonal snowpack on the Sierra Nevada mountain range. They're very small changes in the system. If you look really closely at the data, you can see seismicity rates, slightly increasing, slightly decreasing seasonally, but it's a pretty small effect. So I think largely climate change doesn't have a big impact on earthquakes.
So that's one piece of good news, is one thing that might not be affected by climate change. Okay, I wanted to move next to volcanoes, because although you could make a rough connection in your brain if you're not an expert, obviously for you it's tightly connected to earthquakes. So how should we think, where do volcanoes come from, and how should we think about them vis-a-vis earthquakes?
Well, I'll describe one type of volcanoes which also occur in subduction zones. So again, that plate is diving down. It's bringing down certain minerals, and when they reach high pressures and temperature conditions, certain set of conditions, certain components of those rocks begin to melt. And then that melt percolates up to the surface and forms an arc of volcanoes. So, example would be the Cascade volcanic range here in western United States.
So the red stuff that we see coming out of the ground, forgive my simplicity, the red stuff we see coming out of the ground, the lava, that is basically the result of friction between the plates and melting?
Friction may play a small part in it, but it's probably not frictional melting. It's just different rocks undergoing different phase changes. And the chemical structure changes, and then suddenly, rock that was stable as a solid, under these conditions, it transforms, and now it turns into a liquid, and then it migrates upwards.
So as a physicist looking at both earthquakes and volcanoes, is it the same phenomenon, the same modeling tools that you use, or are they very different modeling approaches to think about volcanoes versus earthquakes?
Well, so my group's interest in earthquakes would be how they occur, how they radiate seismic waves. My interest in volcanoes is trying to figure out what's happening inside a volcanic conduit where you can't put instruments.
Right.
And we try to figure that out using the waves that a volcanic eruption produces. And so those would be seismic waves that go through the solid earth and create shaking of the ground, or it would be low frequency sound waves called infrasound that go through the atmosphere.
I see. So there is kind of, I don't know if you call it an earthquake, but there's elements of a volcano that are very relevant to earthquake studies because they are movements of Earth, and it's the same kind of physics that's
exactly
involved.
Right. Understanding how rocks deform, respond to stress, and if they do that rapidly enough, then they do generate waves.
So just to make a little tangent, but I think it's a relevant tangent. I was at a talk recently from a guy who had a hypothesis about a big earthquake in North America, off Vancouver and Seattle. That there was evidence that this had thought to been an earthquake, a relatively silent earthquake area. But I believe he was looking underwater and saw changes in the ocean floor that made him believe that there had been a history of huge earthquakes off the Seattle-Vancouver coast. What's the status of that theory? Because I think that's very exciting and interesting to especially people living up in that area of the country.
Certainly. Well, it's only actually been in the past couple of decades that we've recognized that the Pacific Northwest region is a subduction zone and it's capable of magnitude 9 earthquakes. So there's a really fun story that played out where scientists discovered that there was the last of these large magnitude 9 earthquakes was back in 1700s, and they did it by having accurate records of large wave arrivals in Japan across the Pacific.
Yes,
Ocean.
I think he mentioned this, and that was, and now the question is, are we getting ready for another one? And of course, that's where the prediction is hard, but we might be able to at least focus attention on what's going on in those areas. This is The Future of Everything with Russ Altman. More with Eric Dunham next on SiriusXM Business Radio Channel 132. Welcome back to The Future of Everything. I'm Russ Altman, and I'm speaking with Professor Eric Dunham of Stanford University about computational modeling of earthquakes. Next, Eric will tell us about an interesting zone in the northwestern United States called Cascadia, where the subduction zones are doing things that are not what's usually observed. They're providing insights about how local conditions can cause multiple small earthquakes versus a big single earthquake.
Right, so Cascadia is a subduction zone. It's offshore Oregon, southern Oregon, all the way up through Washington State, up into British Columbia.
And what have you been looking at, and what have you been learning?
Well, so the Cascadia subduction zone, most of the region that would have a big earthquake is coupled together. But what's pretty interesting is that just below that, now the part of the fault that's underneath land, it was discovered about 20 years ago that the fault intermittently, about once every year, slips, but slowly, so it's maybe 100 times faster than the typical rate of plate convergence, which is how fast your fingernails grow, but it has these intermittent slip events that can last weeks or maybe a month. And so what's really unclear is the relation between these so-called silent earthquakes or slow slip events and the larger earthquakes.
Okay, and this goes right to your point earlier in our discussion about, there are these models that they stay fixed for a long time, but there are other models or other physical realities where it's more, fluid almost in terms of the rocks and their relationships. Do we know which one is going on here in Cascadia?
Well, we do know that something interesting is going on down below. It's interesting that you brought up fluids, because one of the leading hypotheses for what's happening in this region, why the plate intermittently becomes decoupled and slips just a little bit, not enough to create ground shaking, but just a little bit, is that fluids that are being released by certain reactions where rocks change type, fluids are released in that process, and then they migrate upwards along the fault zone, and they're changing the pressure in the fault, they're causing the rocks to dilate, expand, and that changes how easy or hard it is for the fault to slip.
Yes.
And so one idea is that there are these pressure pulses moving through the fluid that are intermittently slightly unlocking the fault.
Well, so that's very interesting, and I can see how a computational simulation might allow you to imagine different worlds and different options, and kind of say which of these. I presume that there are sensors here because you've been talking about the sensors. Which of these are matching our sensor data more accurately? Right. Well, okay, so we're in this phase. I just want to the questions that everybody has. I just want to try to ask them. There is a history of these earthquakes in central United States that which is not thought of as a seismically active. How do we make sense of those currently? Are those a big enigma to folks like you, or does it kind of all make sense and there's no big question marks there?
So it's all about fluids when it comes to the central and eastern United States. And so oil and gas production, anytime humans inject or extract fluids, they're changing the pressure of the fluids underground.
Right.
And so that region does have, the rocks have deformed and bent and stretched, and they built up some energy over time, but it's not the boundary between tectonic plates. And so what it took was, fluid injection and extraction activities to change the pressure on these faults and to suddenly pop off earthquakes to trigger them.
So that's very interesting. Tell me if I'm getting this right, but is it fair to say that human activity then can impact the likelihood? Because I'm struck because before I was asking you about ice and about water, and you said no, those are really very small. But it sounds like in this case, even good old-fashioned humans are able to make perturbations that change the seismic activity. Can you just say a little bit more about the kinds of things that do these things worry you? Are there human activities that make you, as an earthquake person, worried that we might be playing with fire, so to speak?
It's certainly of concern, right? The buildings in the central United States are not built to withstand earthquakes, right? So when the rates of seismicity started, increasing a decade or so ago, our field as a whole turned its focus there, right? And that's where a lot of the basic work on understanding how fluid injection and extraction changes pressures, if that actually will trigger earthquakes or not. Our field really devoted intense effort to that.
Yes, very interesting. So I do want to have a few minutes about tsunamis. You made a really interesting comment earlier about how these earthquakes off the coast of northwestern United States, one of the pieces of evidence were, I think, Japanese records of arriving waves, and then you could kind of back calculate, oh, that wave must have started here, and that's the earthquake. So, and I think many of us are now much more acutely aware of the relationship between earthquakes and tsunamis because of the devastating ones that we've seen. Are there interesting physical modeling challenges there? Is that something that just happens, or do you find is it useful for you physicists with your computational modeling skills to actually look at I guess the question would be, can you back out information about the earthquake from the nature of the waves that you're seeing hitting the shore?
Right. So what we're about to embark on is densely instrumenting the Cascadia subduction zone, getting good seismic images that constrain the structure, measuring the slow deformation to figure out how the rocks are, what parts of the fault are coupled. And then we put all that together and run simulations. Here's what an earthquake would look like. Here's what a tsunami would look like. We can do this retrospectively in the past too, and then try to calibrate these models by comparing to, let's say, a sand deposit that was washed on shore from an earthquake or tsunami hundreds of years ago, right? Can we match the timing of these deposits to get a sense of whether our models are being set up correctly and with the right parameters?
So that sounds great. So let's take a minute to take me through this sand deposit. I mean, I didn't know about this. So what is it that you actually measure, and how do you relate it back to the historic events?
Right. So the goal is to figure out where tsunamis occurred, which are coming from large earthquakes, and how large they are. And so a tsunami will, it's a very rapid flow of water. It's mixing up the sand in it. So it's turning, and it transports that sand onshore, right, as the water comes in and inundates. And then some of that sand falls down and is left as a layer. And so then over time, if you've had multiple tsunamis, you have layers. So there's these thin sediment sheets that can be seen either through excavating or drilling or
so
such.
you can resolve the different layers, and I guess that's my surprise is that as an uninformed person I think, oh well, there's sand on the beach, no surprise. But what you're saying is that these events create discrete layers that can be separated from other discrete layers. What's in between the layers?
Well, imagine that this happens in a lake that's on shore, right? So there's naturally mud that's accumulating in the lake,
Right.
and suddenly there's a sand layer. And then more mud, and then another sand
Okay,
layer.
so the nature of the mixture changes, and then
Right.
it gives you this. And I guess you can also are these datable?
They are, yeah, through
Okay,
the organic material that's
Right.
in the
So you can get
in the mud.
okay, very good. And so in our last couple minutes, I just want to get a good idea of what are the challenges or what are the exciting new directions that you're seeing. You've mentioned the sensors. You've mentioned these new areas that are attracting your attention because they might have a slightly different set of physics going on. What would in the field of earthquake and seismology, what are the big challenges that we should expect to be hearing about in the next 10 years?
So I think computation is going to be a large part of this, right? Computation and modeling, that's where you put all the ingredients together. That's where the data comes in, it constrains the model. We connect with laboratory experiments on frictional properties of rocks that were collected by drilling down across the fault. We connect with what geologists see in subduction zone rocks that have been brought up to the surface millions of years later, right? We synthesize all that together, and now we can finally do that in 3 dimensions.
Yes. Will these findings lead to policy recommendations? So, you're a scientist. You're trying to understand this physical phenomenon. Do you get calls from governors or leaders of nations wanting to know how the findings of your field might impact policies about building and infrastructure?
Certainly. So, some of my work, particularly as I was starting here at Stanford, was very much focused on using these earthquake simulations, calculating ground shaking, and passing that off to engineers who then run that shaking through a building. Does the building withstand it or not, right? And if there's not enough records of large earthquakes, you turn to simulations to fill in that gap. And so I think the same thing will happen with these, or is happening with subduction zones. The last big event in Cascadia was in 1700s, right? We don't have data for that. We have to turn to simulations to understand what to expect.
And that might give, I'm presuming that would give advice both about the type of building you might want to create and the type of tolerances of that building, but also where to build and where not to build, perhaps. Is that
right,
true?
Because these models also connect, it's not just the earthquake model, we're also modeling the coupling from the solid earth to the ocean, the tsunamis. We're making predictions of how large the tsunami will be, how far inland it will go, how deep the water is, right? And so then you map out inundation zones and you have different building codes within an inundation zone and outside it.
Thanks to Eric Dunham. That was The Future of Earthquakes. You have been listening to The Future of Everything with Russ Altman on SiriusXM Business Channel 132.